Welcome back to part 2 of the second lesson in chapter 4. We now are going to learn how to convert between degrees to radians and then radians back to degrees. So the way I like to remember it is if I'm going from degrees to radians, then I'm going to multiply by pi over 180. And I want to get to radians, so my radian value is in the numerator. Remember how pi equals 180, so this is equal to 1. So this is the conversion between the radians and the degrees. Now if you want to go from radians to degrees, then you're going to multiply by, you're just going to flip that, 180 over pi, so that the radian values will reduce and you will be left with degrees. Let's try an example. So if I want to go from 210 degrees to radians, I want the equivalent value in radians. I have 210 degrees, and I'm going to multiply that by pi over 180. When I do that, you'll notice that the degrees are going to cancel, and you will be left with 210 over 180, which reduces to 7 pi over 6. Now if you notice I left the pi and I did not give a decimal value. It may want you to give a decimal radian value, but usually we're going to leave everything in the pi value. Now if I have a negative pi over 6, remember that would be going in the clockwise direction. I want you to write that in degrees. So we have negative pi over 6, and we're going to multiply that by 180 degrees over pi. Well, our pi's will cancel, and that's what we want to happen so that we are left with degrees. 6 into 180 is 30. Don't forget your negative. Okay, so you have negative, that is negative 30 degrees if I go in a clockwise direction down to pi over 6. That's a negative 30. Another area that we're going to talk about are different ways to identify the angles. So when you have an angle, and we'll go back to kind of our initial side, and this was the terminal side, remember? If you notice, here's my angle, but I can name that angle going this direction, which is the positive direction. That's 135 degrees. That's also, if you notice, if I draw a little cross here, okay, you notice that, remember, that would be 0, that's 90, that's 180, that's halfway, that's at 135, it's 3 pi over 4. But also, if I come in the negative direction, the clockwise direction, that would be a negative 225. If I have negative 225, if I notice if I add both of these, what value should I have? That would be all the way around the circle. That gives me 360. That means I did it right. Okay? There are two different ways to name every angle, in the positive and in the negative. These are called coterminal angles. Okay, that means that you have the same side, you're just going in the different direction. So sometimes I will give you an angle and I will say, list the coterminal angle. Well, you would subtract it from 360. And then you would have the other coterminal angle, whether it's the positive or the negative. Now you can also spin around a circle or around the angle. Think of it as kind of when you look around a screw, how it just spirals around, kind of like a slinky, how it keeps going round and round and round. Let me get another color here. If I spin around here, so that if I start here on the initial side, and I go around the circle once, I go around the circle again, and then I end up right there. So I've gone around it. If you notice, I went around it. I did 360. I did another 360. And then I did 135. Okay, that got me to 855 degrees. And you can do that. You can keep spinning and spinning around, and you will have different multiples of 360 plus the theta, the angle that you are dealing with. We were dealing with 135. Now you may want to write that in radians. You can do that in radians. Instead of 360, I may want to say 2 pi or 2 pi. I added 2 pi and then another 2 pi plus the 3 pi over 4. Well, 2 pi, if I have a common denominator of 4, right, that's 8. 8 pi over 4. So I have 8 pi over 4 plus 8 pi over 4 plus 3 pi over 4 gives me 19 pi over 4. So then I have multiples of 2 pi, and I added my theta. So sometimes when you spin, you can have them larger than 360. That just means you're going around and around and around, and you can go around multiple times. All right, now we're going to look at some formulas, and this is the last part of that's there on that sheet I handed you in class. I'll be right back. Yay, more formulas to memorize. You already know some of these, but let's review. If you have the arc length, and we talked about this earlier, you have the arc length, which we refer to as S, equals the radius times the theta. Please keep in mind that the theta is always in radian value, which means your pi values. Then you have a linear speed of an object. That's the length traveled over a period of time, like miles per hour. And that's going to be referred to as your V, which is going to be the arc length, see they're related, divided by the time. And you can sometimes just substitute that in there. R times theta divided by time. You also have what's referred to as angular speed. Well, that's the rate that the object rotates over time. So you have the length of the traveled length it traveled over time, and you have the rate that the object rotates over time. That's the difference between the two. This would give you revolutions per minute, for example. Again, pay attention that the theta is always in radians. So this means that if you're given degrees, you're going to have to do your little conversion to make it in radians before you can plug it into your formula. So keep that in mind. This little symbol here may look like a W, but that really refers to a Greek letter that we call omega. So when you have, and I'll write that in here for you, that is omega. So you've got theta and you have omega. We introduce a few of these Greek letters every now and then. But that is the rate at which the object is rotating over time. Then you'll also have the area of a particular sprinkler that's running is a very common one. Anytime you want to figure out the area within a circle, area of a sector, you're going to take 1/2 of the radius squared times the theta. Again, your theta has to be in radians. So let's do a few examples. The first example I have is to find the arc length if you're given that theta is 2 pi over 3 and the radius is 2 meters. All right, I was nice here. I already gave it to you in radians. So you would use your formula, arc length, which is S equals R times theta. And then when you work that out, you're just going to have the arc length equals 2, my radius, times 2 pi over 3. Well, that's 4 pi over 3, which is about let's say 4.2 meters. And depending upon what you're doing, what you're making, if you're building something, you can't go to Home Depot and say, I'd like 4 pi over 3 of this, right? You have to say 4.2 meters, or you'd say 4.5 meters. So you're going to have to do the conversion at some point. Example 5. Find the angular speed of a DVD with a diameter of 120 millimeters in radians per second if it rotates at 3.5 revolutions per second. All right, so I want angular speed. That was omega equals theta over t. That means that I'm going to have my revolutions per second. Okay, I've got 3.5 revolutions per second. Let's see, theta equals 3.5 revolutions to 1 second. And one time around my circle, right, 2 pi is equal to 1 revolution. That way, my revolutions cancel, and I'm left with radians per second, which is what I wanted. Right? So that would equal 3.5 times 2, so I've got 7 pi, which is approximately 21.99 radians per second. Now, if the DVD player overheats and it slows to 3 revolutions per second, find the linear speed in meters per minute. All right? So that would be if let me scoot this up a little bit. So if it is slowing to 3 revolutions per second, and I need to get from seconds to minutes. So let's do that conversion first, a little dimensional analysis here. So I know that if I have 60 seconds, my seconds is down here in the denominator, so I want those to cancel. That's 1 minute. Now I've got my minutes in the denominator. That's where I want them. My seconds are now gone. That's good. Now I need to change my revolutions to meters. Well, again, if I have the revolutions are going to be the 2 pi to 1 revolution, right? And that also is, let's see, 2 pi r. That gives me my whole, if I go around, if I'm getting the distance around, that would be the circumference, right? So I need to figure out what my radius is. We didn't do that yet. The diameter here was 120, so my radius is 60. Okay, we need to figure that out. So here, if I have 2 pi times, and I'll put the 60 here, so you can see the 60 millimeters over 1 revolution, then I would have, and those are multiplied, then now my revolutions have reduced, and now I've got my millimeters, but I don't want millimeters, I want meters, so I've got one more conversion. Okay, 1,000 millimeters to a meter. So now they're gone. And I'm in meters per minute, which is what I wanted. Multiply, divide, you get 67.9 meters per minute. Last problem. The area of a sector, given that theta is 50 degrees, it's in degrees, we're going to have to convert it, and the radius is 6. All right, so our formula was the area is 1/2 r squared theta, and I know that my area is going to be equal to 1/2 my radius, which is 6. I'm going to square that. And then I have 50 degrees. Well, I can't have 50 degrees. I need to convert that. So I'm going to convert it to radians. So I'm going to multiply it by pi over 180. Okay, when you come to class, we'll check your answer. You can do that, and we'll check it when we get to class and do the assignment. Thank you.